right, so in this lovely week, we are going to get into the lovely world of PLCs. All right. Now, throughout this semester, you have all heard me probably say the term PLC, I like 3 or 4 times in class when I'm actually doing a presentation. Anyone remember what it stands for? Close, programmables, right? Okay, programmable logic controller. All right. So it is per se, this is like the brains of automation. All right. Without this, automation can happen. All right. There's an old school way of doing it called relay logic, and it works, but it is a royal pain in the butt. All right. So this, depending on how you look at it, either complicates wiring or simplifies it. I personally think it simplifies it, but we'll get into that a little bit later. All right. But anyway, programmable logic controllers. All right. And as a quick get into this. So some of the hardware associated with a PLC. So first we have the processor unit. All right. As you can see here, that is pretty centrally located in the PLC itself. All right. So we've got the processor. All right. This is the unit that contains a microprocessor. Now, for those of you who say microprocessor, and you're like, hey, we've used Arduinos in here. Is this the same thing? In the long run, yes. In the short run, not even close. All right. Does a Arduino contain all of the same things? Kind of, sort of. All right. So we'll come back to that in a few minutes. But anyway, the microprocessor unit interprets the input signals and carries out the control actions according to the program stored in its memory, communicating decisions as action signals to the outputs. All right. So it takes the inputs, reads them, runs through the code, says, hey, here are the new outputs, updates the outputs. All right. That's basically what the PLC is doing. And if you think about it, that's basically what any programmer or microprocessor, whatever, is doing. All right. It's taking information, running code on it, outputting information based on it. Right? So processor. Then we have some sort of memory, all right, and that is where we are going to be storing our information. All right, so that would be up here in the top left corner. All right, now let's say program and data memory. All right, so the program is the program that you actually wrote that's saying, hey, when this button is pressed, turn this output on. This temperature sensor goes true, turn off the heater, or whatever the thing is. All right, the data memory is like, hey, the temperature is 50 degrees Celsius, or whatever the magic number is that you're trying to store. All right, so we have 2 different types of memory. All right, next we have a power supply. All right, it's down here at the bottom. All right, notice that we've got that going to the inputs, we've got to go to the outputs, we also have to go straight up to the processor. All right, and this is needed to convert the mains AC voltage to low voltage DC. All right, now here's the interesting thing here. The voltage that you use is going to vary. Right. For example, this PLC. Now, that voltage, I just said 24 volts DC. All right. Have I told you guys why we like 24 volts DC? All right. So, when you're working with voltage, right, if you guys take 120 volt wires, come out the wall, and you touch it, you shock yourself, right? All right. Probably many of you have done that by accident. You're trying to push a plug in, you touch both prongs, it zaps you real good, or whatever the case is. You've probably been shocked by electricity before. Right? And that's all not really good, but I mean, you survived, so that's good. Applaud you, right? But 120 volts, that shocks you. And now, you might be going, why does 120 volts shock me? But if I touch the car, my battery in my car, my 12 volt battery, and I put my hands on both terminals, I don't get shocked. Anyone know why? All right, it's the resistivity of your skin. All right, so you need to have so much current flowing before you feel the shock. And those who don't know, we have Ohm's law, which is V equals IR. Volts equals current times resistance. Right. If you know the resistance of your skin, which is overall pretty easy to measure, you go to get any voltmeter and touch it between two places on your body, and it should give you a resistance measurement there. But once we reach like 30-ish volts, that's when you're going to start feeling the shock. All right, so 12 volt DC that you have in your car, below 30 volts, that's why you can touch both batteries and not shock yourself. Is electricity still flowing through you? Technically, yes. But your skin resistance is so high that you don't get shocked. 120 volts coming out the wall is high enough that the resistance is high enough, or the resistance in your body is low enough, so 120 volts that's high enough that you feel the current flowing through your body. That's why you get shocked. All right? So it's this like really weird game that you're going to be playing when it comes to these things. Now, traditionally, 30 volts is like the safe point. Right? 30 volts or less, you're traditionally not going to feel the shock under normal circumstances. Right? Why do I say under normal circumstances? How many of you have looked at 9 volt before? I have. No one else? Really? You've never gone, is this 9 volt good? No. You put it to my tongue? I feel like I get some 9 volts out there. But anyway, if you look at 9 volt, you get shocked if it's got enough voltage still. Why does you get shocked with a 9 volt, not 12 volt car battery? What? Yeah, your tongue is wet. Yeah. So the resistance is a lot lower now. Hence why I say under normal conditions, right? If you have not wet soapy hands, if you still have wet hands, like raining out, you're like, oh, you took my car battery, you might shock yourself. All right? So you do need to be careful in those circumstances of not like touch things when you have wet hands. That's also why it's like standing in a giant puddle and working electricity is a bad idea. All right? So there are lots of situations with like the 30 volt rule. I don't even call it a rule, or general knowledge. That 30 volts is, below that you will still feel a shock. Right, so we do need to be careful with that. Now, I do have in my notes that you maybe go down as low as 5 volts, 3.3 volts, 1.1 volts. All right, not as your main signaling, but like on the computer itself. All right. Any of you who are big into gaming or overclocking your computer, you're knowing that you apply a voltage to the core of your CPU to make it run faster. All right, and by doing that, you're creating more speed. But anyway, you're like, oh, let me overvolt it to like 1.2, 1.3 volts. That's what the core of your CPU is running at, microprocessor. All right, it doesn't need the whole 5 volts. All right, it's running at 1.1. So depending on the microprocessor, it may have 1.1 volts going to that. It may have 5 volts happening for other things. You may have 24 volts happening for your signaling. And all this is happening inside the PLC itself. So all either feed 120 volts in or 208 volts or whatever the case is, and all is well. So you just have to know what voltage you need to input, and the PLC will take care of the rest of the voltage. Right? So you do need to know what voltage it is that you're working with, and be careful with that. Now, having said that, all right, yeah. Anyway, we'll move on. Come back to that later. Next, we have our inputs and our outputs. And if you notice up on my slide here, they are 2 different sections. All right, we've got inputs, interface on the left, we've got output on the right. Typically, that's how you see it. If we look at this PLC, all right, you're going to need to have some sort of programming interface, and I'm going to go through all these things again. But anyway, communication and programming device. So let's just, I guess I'm not going to go through quite all. But anyway, we'll come back to this. So we have our input or output. All right, this is our real-world interface to the outside world. And most of the time, these are going to provide isolation and signal conditioning. All right, what I mean by that is we need to protect the main PLC. We're expecting voltages coming in on these things. How do we make sure that they're not going to damage the PLC itself? And that's with isolation and signaling conditioning. So up here on the right, we have an example that shows an opto isolator. So you would have your push button here. So you'd have your 24 volts comes over to a push button, comes in here, and then it would come out here, and then this would go to 0 volts, ground. All right? And when you push that button, this little LED light would light up, and that would send signals over here to a phototransistor, something that is light sensitive. So when the light hits it, it says, oh, I've got signals. So there is a physical air gap between these things, between these circuits. Is it a large air gap? Yeah. All right. But like this is all happening inside a little dip, like a little dip chip that has maybe 16 pins on it or something like that. All right. So really freaking small scale, but it's enough. All right. That, and it's all probably potted and whatnot. So you've got like epoxy with the clear lens with epoxy like all surrounding it. So the only physical way out is from the light. There's no way for electricity to go from side A to side B. So we can use opto-isolators for those types of things. Right? And that could be done on the input side, it could be on the output side. If we really need to do it more, we need to isolate the inputs because that's where we're like taking some sort of signal and sending it to the microprocessor. Right? On the output side, we normally have, as it says down here, 3 types. We've got relay, transistor, or triax. Now, anyone heard of any of these things before? No? Haven't got there in 110 yet? Okay. That's fine. So a relay is just a mechanical switch. Alright? And I do actually have one of those. Let's see how this is going to work. AC or DC. So you could control it with DC, and then the output will be AC. Or it could be DC, doesn't matter. Right? The downside to a relay is it's a mechanical device. So there's physically something moving inside that's clicking and unclicking. Every time you open those contacts, if current's flowing through, there's a little arc that forms that hopefully just breaks at some point when that contact moves far enough away. All right. However, that arc causes pitting on the contacts, so that means that it can go bad over time. All right. Now, luckily, they have kind of thought about this, and we. Side effects. Right. Now, when I say relay and PLC, I'm not actually talking about one of these. Right? They're actually built into the PLC itself. They're little black boxes. You can't replace them very easily. All right. Could you replace them? Technically, yes. All right, but actuality, it's a bit harder than that. But anyway, so that's a relay. You also have a transistor. Now, transistors and triacs are solid-state devices, which means there's no physical moving anything. Right? You send a little control voltage to it causes a bias to one side, which allows electricity to flow another way. Right? This is not an electricity class. It is, but we're not focused on how transistors and triacs work. But transistors are for DC. All right, triacs are for AC. All right. The reason that triacs don't work on the world of DC is when you first give the signal to a triac, it does its thing, allows electricity flow. But when you remove that signal to say, hey, let electricity flow, it stays on until the device turns off. All right. And for DC, the device will never turn off, right? You're applying power to something like a light or a relay or whatever, it's going to stay on. However, in the world of AC, since we're going 120 volts, negative 120, up and down, we hit a zero crossing point where there's no voltage, which means the device is actually off. So that's why triacs work with AC. All right. Triacs. Transistors, on the other hand, when you turn them off or go off, however, they only allow current to flow one direction. So with AC, since we go negative, current's flowing the opposite way. Transistors don't work in that aspect. All right, so they are DC only. So relays do both AC and DC. They are mechanical, which means there is physically something moving. All right, so that's a downside. There's a wear component there. Transistors are good, but they are DC only. Triacs are good, but they're only AC. So they both have their pros and their cons. So we do need to make sure we have the right output chosen for the specific circumstance. All right. My voltages up there, I do have 5 volt, 24, 110, 240, 208 might be another one. There's also 400 and stuff. All right. Also, have you guys heard of single phase and three phase? Yes. All right. If you haven't, all right, that's fine. So, all right, in the world of AC, we have, that's horrible, but we have this, going on. That's what our power looks like. That is single phase power. There is one voltage going up and down compared to neutral. All right. If we go to the world of three phase, we now have 3 of these. So let me just go ahead and change my color here. So it's yellow. So then you would have another one doing that same thing. We're just a little bit off. And then again, we would have green. We would have another one that would start like here, doing that same thing. And I'm sorry, I'm horrible at drawing these. But they're what we call 120 degrees apart. So they start 120 degrees apart. So power is much more consistent. As you can see here, from peak to peak, from here to here, it's a very small distance compared from there to there, right? It's 1/3 the distance. So three phase allows us to have much more consistent power for large current draw devices like motors and things like that. Motors and heaters and things like that. Something that's extremely large draw. Three phase power is better. All right. In your homes, unless you specifically need it and get your power company to run you power for it, you're not going to ever have three phase, or you're going to have an adapter that goes from single phase to three phase. All right. There are things out there that will do that, but for the most part, we don't have three phase in our houses. All right. Single phase in our homes, perfectly fine. You do have 240 volts in your house, or 220, whatever you want to call it. All right. And that's what we use our high-draw applications for like washing machines, if they're not washing machines, dryers, if they're electric, water heaters, HVAC, those types of things. For me, my cable saw, I also run off 220 because I can. It's a better system, lower current draw. So that is what I have chosen to do. All right. And then the last thing that we have to think about when it comes to PLCs is sourcing and syncing. All right. Now, you're probably really confused by that, and I don't blame you. It still confuses my PLC students when I ask them, is that sourcing or syncing? All right. So if we look here in our picture, we have two very slightly different pictures. What's the difference?
Input and output or switch.
Yes, all right, not the best language, not the input and output, but where the input device is. All right, on this one, you can see the input device is on the positive row. On this one, it's on the negative row. All right. So the one on the left, which is A, is a sourcing input. All right. which means the module itself, the input module, is actually supplying 24 volts, and it's trying to detect when that voltage goes to 0. All right? So the logic is actually kind of backwards. Over here on the right, this is our syncing, which I would say this is more your traditional, in my opinion. All right? Your input device is on the positive line, and the input module itself is directly connected to 0 or negative volts. All right, so in a sourcing, the input module is supplying 24 volts. In a syncing system, the input module is directly connected to ground for 0 volts. Negative. All right, so that is the whole difference there. And it's just, am I looking for a 1 or am I looking for a 0? What's true? That's really what it comes down to. And you do need to be aware of this, because for like a normal push button, it doesn't matter. All right, but if you have a proximity sensor that doesn't involve contact that's powered, that is an NPN or a PNP transistor, then it matters. All right, so it's really quite annoying in my opinion at that point, but that's just the way this game goes. You don't have options sometimes, so you got to make sure you pick the right one. Next, we go to the PLC system itself. All right, so on the left, or again, as this picture shows you down here on the bottom here, this is what would be a truly modular based PLC. All right, this is you building it for exactly what you need. All right, so this first module right here, this is everything related to the brains of the PLC. All right, so this is where your microprocessor is. This is where your RAM is. If you notice right here, we actually have a little expansion slot for a little SD card or something, so we can actually add some more memory to it. We've got our programming interface. We've got an Ethernet, and we also have a serial down here at the bottom. All right. Our power supply is actually technically right here next to it. All right. It does only take 24 volts in though. So this is really just more like a power input than a true power supply, but it's doing conditioning and taking that 24 volts and supplying 3.3 volts or 5 volts or whatever other out signals it needs. And then next to this, we start adding our modules. So here we have our control net, our device net, sorry. Our device net module, then we have an input module, then we have an output module, and here's our analog module. You guys can't really read my letters, but so let's try this again. Input, output, analog. All right, and we could keep stacking these. You could do a high-speed counter one for an input or whatever the case is. All right, so this one you are really building it specifically for your needs. All right, now the nice thing here is when you burn out 6 of your outputs on this card because you have silly tech people who don't know what they're doing, or stuff has just failed or whatever the case is, all right, you can literally just replace this one output module. So you'd go, okay, let me just replace that one module. You pull it out, you put a new one in, you move on with your life. All right. On my all-in-ones over here, take going on here. So are the singular or the all-in-ones going to be probably a better bang for your buck? Yes. Are they going to fit your needs exactly? No. All right. So you have to have a little bit of give and take going on. You have to know what it is you need. What are you trying to accomplish? Does that one have everything that I need it to have? All right. So those are the games that you have to play when you're picking a PLC. All right. Now, when it comes to our input types, you've already heard me talk about analog, or you just heard me talk about analog. All right. Most of our inputs that we're using are what's called discrete. All right. Those are on or off, zeros or ones, true or false. All right. So that would be a push button or a proximity sensor. All right. And that's said, like mostly what you're probably going to use. That's what all the ones that I pointed out to on PLCs work. All right. You also do have those analog, and those give you a value between, say, 0 and 100 or 0 and 1,000 or whatever the case is. All right. Those would be like temperature sensors. Now, could you have a discrete temperature sensor? Yes, you could. All right. You could say have a temperature sensor that's like when it's over 95, you're true. When it's under 95, you're false. And as long as all you care about is whether you're greater or less than 95, that works perfectly. Now, if you care about, you're doing a process and you're like, I need more precise control. I need to stay at 95 degrees. So when it reaches 96, I want to turn off. When it reaches 95 and a half, I want to turn on. So that way it stays in this nice little window. That discrete sensor of greater and less than 95 probably ain't going to do it for you. All right. So that's when you need the analog. You need to know, oh, it's 95.3, 96, whatever. You know, that's where the analog would come in. All right. You also have digital inputs, and those are going to be more like your serial communication. Those are sending pulses, on and off, ones and zeros. All right. So that would be an example of a digital. All right. Our input modules, they could be AC or they could be DC. You could have an input module that is actually taking 120 volts AC into it for a true signal. Most of the time we're not doing that because, again, safety. 24 volts is much safer for you to work with. It's safer for you to have in a box for an electrical connection for accidentally shorting or something. So we like the world of DC inputs better for safety purposes. But you could have AC inputs. I've heard of like equipment that companies have bought, and they're like, yeah, right on the PLC, you know, they've got these add-on modules, all right, and one add-on module will be AC, and one right next will be DC. And they're like, yes, I don't know why, but this push button's AC and that push button's DC. I'm like, that is really stupid. And they're like, yes, it is. Okay, I'm glad we all agree on this. All right, but that is possible to have. So you just have to be careful when you're working with this stuff, knowing, oh, it's an AC or a DC system. All right, so please be aware of that. All right, we've already talked about sourcing and syncing. All right, now getting a little bit more into the world of analog. All right, when we take an analog input, we have what we have called is it's the accuracy. All right, so how many bits are we using to determine how that analog input? All right, I need to tell you what this analog value is. All right, and we normally do that with a analog to digital converter, an ADC, analog to digital converter. All right, and normally they'll tell you it's an 8-bit or 6-bit or a 10-bit or a 12-bit ADC, and what that's telling you is how accurate we can be. What's the resolution of this counter? All right, so here you can see that when it's all zeros, you know you're at the 0 line. When it's all zeros at the last one, you're a 1, you'd be up here at the value of 1. This would be the value of 2, and then 3, and then 4, you know, all the way up the line. All right, and this is just counting in binary. Now, how many bits is the resolution? It's how many times for the voltage range that is acceptable how many ways can I divide that? So if I have an 8-bit, you can divide that by 256 different steps. All right. Now, when you are using a temperature sensor that's between 0 and 100 degrees, actually, let's just go 0 and 256 degrees. All right. That means you get 1 degree increments. All right. Now, let's say you need more accuracy than that. What do you think you do? You have two options. Option one is you buy a different temperature sensor. So instead of 0 to 255, say you only really care about 90 to 100, you would say, okay, give me a 0 to 125 degree, 125 degree temperature sensor. Now I have half degree increments because I have 256 steps over 125 degrees. It's roughly half degree increments. All right, so you've now doubled your accuracy. The resolution is still the same. You still only can do 256 different steps. But because our range is smaller, we have much more accuracy. The other option is you buy a better ADC. So instead of an 8-bit, you say, well, I need more accuracy. Let's go to a 10-bit. Well, instead of 256, you now have 1,000 different steps. 1,024 to be exact. All right? So now, for that same 0 to 255, you now get quarter degree increments. All right? So there's a lot going on here when it comes to world analog. Okay, what do I need to measure? What do I care about measuring? Can I restrict my sensor to be more in that range that I want? All right? And picking sensors is a royal pain when it comes down to it. They're also, as far as I'm concerned, more expensive than they need to be. But that's a problem for another day. All right, so that's the wonderful world of analog. When it comes to our outputs, we've already talked about relays. All right, so up here we would have a relay. There we go. So you can see we've got our coil here, and when that coil energizes, it would move this away, and then when you de-energize that coil, it would move this bar back. So it's physically connecting and disconnecting. All right. Notice we still are using those opto-isolators. All right, so we're still protecting our PLC from possible voltages coming in backwards somehow. All right. If you're using a triac, same idea. All right, except for we've got an opto-isolator to our triac here. All right. So once we energize this, power can now flow, go through everything, and then it flows out through our load. All right. Then it can go backwards as well. And same thing, except for this last one uses a transistor. So it's, again, wired basically the same way. Not quite exactly, pretty close. All right. And that's what's going on there. So, and then our analog outputs. Our analog outputs look a lot like the ADC, except for it's in reverse. So you would put zeros and ones in all of these spots, and then it would actually then convert that to a pulse, power at so many volts. All right, so we can do that backwards. All right, now when it comes to remote connections, you should all start getting familiar with this point. All right, we've already talked about serial. All right, which obviously, hopefully, is what I have right here. All right, so serial is our way of communicating. All right, we've already kind of killed that one real good. All right, remember to make sure you have your baud rates and things like that set correctly, and also make sure it's the right one. So remember, we've got RS-232, which is what we've talked about. You've got that TTL, which is only 0 to 5 volts instead of negative 25 to 25 volts. You also have RS-485, which is differential signaling, right? So we've got twisted pair, all right? So it's still a little bit different on top of that. All right, so you got to make sure you've got that. You have parallel, which we haven't actually talked about parallel. All right. So what parallel does is it allows multiple paths for us to send information. All right. So let's say, for example, I'm doing serial, and I've got my transmit line here. Over here it's received. So this would be the PLC transmitting, and over here it's the scan. I don't know what the device is. All right. Let's say our baud rate is 1 bit, so we can send 1 bit a second. Now, obviously, we're not actually doing that, but we're going a lot faster. Let's say we're doing that. That means every second we can send 1 bit of information. It's not very fast. What if you send more? Yes, okay, we could increase the baud rate, but you get to a point where you can't increase the baud rate anymore because of distance or speeds or whatever the case is. Right? What parallel does is it says, okay, I've got TX1, I've got TX2, I've got TX3, and I've got TX4, basically. And I've got receives for all those as well. So now instead of, we've still at the same baud rate of 1 bit, but we now have 4 lines that we can send information on. So we can now send 4 bits of information at the exact same time. So that's what parallel is. If you guys ever remember old school printers before USB, they were these really wide connectors that looked like BB9s, except for they had, I think, 25 pins on them. All right, those were all parallel ports. So you literally had, to get the information to the printer quick enough, we had to have multiple lines that we could send information on. So that's what parallel would be. We also have Ethernet. And as I told you guys, Ethernet is kind of like the go-to standard overall at this point. All right. This Allen Bradley that I have here has an Ethernet port on it. The Siemens that I have over here that I showed you first has an Ethernet port on it. All right. In fact, this Siemens, that's all it has. It has an Ethernet. There's no serial port. There's no USB port. There's no other way to communicate with this Siemens other than by Ethernet. All right. The Allen Bradley that I have here has Ethernet. It has USB. And then it also has another communications port that I believe is custom for the world of Allen Bradley. So it's used on older school stuff more traditionally, which you could use to then go to Ethernet or something. I have done that before, but not necessary. So, yeah. Now, wonderful world of binary. All right, you guys have already seen this when we talked about serial and converting binary to ASCII. All right, so that shouldn't be too crazy. Now, how do PLCs actually work? All right, this is how most PLCs are functioning. Not all right, but most. All right, so the first thing they do is they scan all the inputs and copy that into RAM. So they go, hey Brayden, what's your value? Hey Chris, what's your value? Hey Dylan, what's your value? All right, goes through everything. What's your value? All right, puts that in RAM, puts it in memory. Goes, all right, let me run my code. And goes, hey, I'm supposed to turn output 1 on. Let me put that in my memory too. Oh, now I'm supposed to turn output 1 off. Okay, put that in my memory. Oh, output 2's on, output 3's on, output 4's off. Puts all that in memory. All right. Then it says, all right, I ran all the code. I know outputs should be what? Time to update them. And then it mass updates all the outputs at once. All right. Then it does what's called housekeeping in the background. That'd be network connections, deleting files, whatever other things it has to do in the background. And then it repeats this all again. All right. So rinse and repeat. It's constantly just doing that same thing over. Take all the inputs, execute the code, set all the outputs. That is how most PLCs are functioning. Right? And this is somewhat of a problem because my PLC students have done this many times. They'll write code and they'll be like, button 1 true, output 1 true. And then we'll say button 2 true, output 1 true. Well, if button 2 is false, it says output 1 is now false. So output 1 never actually gets turned on, even though button 1 is saying, hey, it should turn on. All right. So that is kind of annoying, but it's also really good. So it's just something that you have to deal with. So that is scanning. So basically an input, runs the code, sets the outputs. Some PLCs will take inputs and then as the outputs change, it'll actually set them. So they're like, oh, output 1 should turn on. Oh, output 1 should turn off. And we'll do that as each line of code is true and false. So it really just depends on the manufacturer, the age of the PLC, those types of things. So something that if you care about, look into, but in the long run, probably doesn't make much of a difference for your application. All right. And then with this, we have what's called cycle time. And this is how fast are we able to do this? Input, run code, output, housekeeping. Input, run code, output, housekeeping. How fast can we do that? All right. And the slower, the better. All right. Because the slower faster. By slower, I meant the less time it took. All right. So, but really, it's truly the faster. The faster you can cycle through that, the better, because that means the more often your code's getting run, which means the more often you're not going to likely to miss a button press or something like that. All right. Basically, everything we do in my PLC class, we're running at like 1 millisecond cycle times. All right, so it's running that code 1,000 times per second. All right. However, as you put more and more and more and more and more rungs in and make your code more and more complicated, that cycle time is going to go up. Maybe to 2, maybe to 5, maybe to 10 milliseconds. Now, maybe go to 10 milliseconds, that's still 100 times a second, and you are 100% correct. All right. But if you have something that like cruising by the conveyor belt only happens for 5 milliseconds, and that's truly true for 5 milliseconds, if your code only runs for 10 milliseconds, you could miss that input. You could miss that sensor going from true to false. So you really want to have your code running as quick as physically possible so that you don't miss those input changes. All right. So we do want to keep that. And what determines that? A, your CPU you're using, which is how fast it's able to run through lines of code. B, how long your code is. That will also affect it. How many inputs and outputs you read. Because if if I have 10 inputs to read, each one takes me 1/100th of a millisecond. Okay, it's 10 hundredths of a millisecond. If I have 100, now it's taking me a whole millisecond just to read the inputs. So you want to be a little bit of give and take going on this. Could you technically have one main PLC that runs like 4 different conveyor belts? Yes, you could. You could keep slapping output modules on until your PLC has every output that you freaking need and every input you need. All right, you could possibly do that. Should you? Probably not. You now have one point of failure. If something happens to that PLC, all of those conveyor belts are going down. All right, again, now your code's taking longer to run because it's happening to run 4 different machines. So it's having to run all the code for A, B, C, and D. So if each one takes a millisecond, now it's 4 milliseconds just to get through all the code. All right, so you are better off separating them to different PLCs and then networking them if they need to talk. All right, and that is again for speed, so how quickly your program's running. It's for redundancy, so if something happens to one system, everything doesn't crash and burn. All right. Now, if conveyor A feeds B with B feeds C, C feeds D, and A goes down, it's still going to affect B, C, and D because they're not getting parts. All right. But still, you want to try to keep that type of thing from happening. So, a little give and take there. All right. I/O addressing of a PLC. All right, and this is the last slide that I have specific for this. All right. When I want to know, and that's the annoying part here. So up here we have older Allen Bradley addressing scheme. So we have input output. So you would say, oh, this is going to be I. And then it'd be rack number for these first two. So you would say, oh, that's rack number 01. Then the module number, oh, that's module 8. And then the terminal number, so it'd be slash like 16. So it'd be I018/16. And actually 16, it probably would be 16. It'd be like 0 through 8, 7. So we'll say 6. All right. That would be their addressing scheme. All right. Now, does that really tell you anything about that input? No, it really does not. In older systems, you actually had to know that input, this whole blah, 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 blah. Okay, that means this screw terminal on the PLC. And then you had to look at your notes and go, that screw terminal is the stop button. Right? In the world of Siemens, we do input output, byte number, bit number. So we would say, okay, now we're going to say this is an output 05.6. All right? And that's how it would look. All right? And this says S5 addressing. We're basically still doing that same thing. Now, notice also here, Siemens, when they talk about outputs, they use what? Q. Why did they use a Q? And no one has given me like this is the reason. I've gotten this is the reason I think it is from a Siemens person. And the best bet is Q looks like an O, but it doesn't look like a 0. Or it does, but in your code, as you can see here, I have output 056. Well, is this output or is this 0? So by making outputs Q, it's now a very big difference, right? It's Q output. All right, so it helps you identify outputs versus zeros a lot easier. So that's the best answer that anyone has given me. Siemens is a German company, so someone originally thought, oh, it's German for something. Like, what's Q for what's output in German or something? And it still doesn't start with a Q. So, still not a great reason. But the best guess is it looks like a 0, but it's, helps identify it from a 0 and a Q. So, that was the best I got. So, that used to be how we would differentiate in our code. All right. However, we've come a long way. All right. PLC programmers have realized that system sucks. Because when you're reading your code and you're like, oh, the problem with input 30/6. You're like, what is input 3/6? And now you have to get your note sheet out. You have to make sure you have the note sheet out for the right PLC, right? It could be conveyor 1 could have a different note sheet from conveyor 2. If they're the exact same conveyors, you can still have them wired differently. All right. So what they've done is either a tag-based system or an alias-based system, and they both mean the same thing. As we all know, an alias is another name for something, right? All right. So a tag-based, or it's really everything's called tag-based, but in the world of Alan Bradley, you will also see it called alias. I mean, it's a tag, but it says the name is alias. And it'll allow you to say basically that you're like button stop, and then basically the tag table says, oh, button stop equals, what is it, Q05.6. So instead of you having to go Q05.6, looking at your code and saying, oh, that's a stop button, now by looking at your note sheet, in your code itself, it tells you stop button or button stop. All right. Now, tags are great and horrible at the same time. Obviously, they're great because they allow you to give a name to an input, so that actually means something in the real world. I mean, that's just especially good when you're writing code and troubleshooting code, because you can be like, oh, let me write the code. I need my stop button. So you start typing stop out, and it's like, oh, you want the stop button or the stop this? Stop it? You know, like that one. You just click the one you want. You don't have to remember, oh, it's IQ05.6. I guess if I said button stop, it should really be an I, not a Q. So let's go ahead and make that an I. All right. The problem with tags is you rely on the person who wrote the program to make good tags. All right. If they don't make good tags, it is just as bad as not using tags. All right. And I've had students who did this to me. I'm like, okay, guys, make whatever tags you want. They should be descriptive, and they're calling it like George and Frank, and they're like, our code's not working. I go over to, I'm like, what the hell is this? I'm like, I can't troubleshoot this code. What is Frank? And they're like, oh, Frank's this. I'm like, what's George? Oh, George is that. I'm like, why didn't you just put that in? They're like, oh, because it's all be funny to give around the names of things. Like, if they would give that program to someone else to troubleshoot, it would take them probably like 6 times as long to troubleshoot it. And if I was troubleshooting that, I'd be going through their code and renaming things. I'd be like, oh, Frank is the stop button? All right, stop button. All right, and, oh, George is, I don't know what name I just used. George is this output. Oh, okay, heater. You know, I would be renaming things. So that way the next time I had to troubleshoot it, everything was better. All right, so tags are great because they do allow you to give descriptive names to things, but the problem is that if the person who gave the descriptive name did a bad job of it, it makes it harder. All right, like, for example, button stop versus stop button. Anyone see any issue with those two different names? They're very similar. All right, but if I'm trying to name the same output, if I was doing I05.6, and I would say, oh, that's a stop button, would you call it stop button or button stop? All right, after having done this for so long and write variables for programs and things, button stop is better. And the reason for that is, if you have button stop and button start and button jog, they all get alphabetically grouped together. Where if you do stop button, start button, jog button, stop and start might be close, but they're not necessarily going to be right next to each other. I mean, they'll be pretty close because STA and STO are pretty darn close to each other alphabetically. But jog, that's somewhere completely different in the tag table. So you could have a whole bunch of different outputs or something between the start button and the jog button. But by doing button first, now it's putting them all alphabetically together. So you do want to think about that, and when you're writing your tags, it's like, okay, what's the best way to organize these things? So your naming scheme is very important. It's really what it comes down to. So you do want to have some nice things there. Okay. Now, you may be going, all right, this is a network class. Why do we just talk about PLCs? And I can't argue your point completely. But the reason we talk about this is because these are the heart of the network. If we didn't have PLCs, we wouldn't need the networking. We wouldn't need to send these control signals to other devices. We wouldn't have to have a network connection that says, hey, remote I/O over there, turn this thing on or off. All right. So that is why we're talking about PLCs. All right. They play an integral role. They are what's oftentimes doing the networking and the communications and sending the Modbus signals or the Ethernet signals or the Profinet or whatever different network signal it is. All right. So you do need to be kind of careful with that. Now, the funny thing to me is, the Siemens, that networks just fine. The Allen Bradley I showed you here, that's Micro 850, will not network to another PLC. It is a lower level PLC, so they've disabled like networking between PLCs. I can do networking between this PLC and a VFD, right? But I can't do PLC to PLC, which just kind of dumbfounds me. Right. Now, the last thing that I want to briefly hit upon today is HMIs. And now this is not in my my notes at all.